Okay. So what did we do so far? We created sigma algebras starting with arbitrary collections. That's a nice task. And let's look at some examples of them, further examples. We have already seen one example. Okay. And this was about throwing a die. So let's look at an example of bacteria. So remember that we looked at bacteria populations, or just one population, in a Petri dish over a day. And your sample space in that case is Z plus because you're interested in the number of individuals in the population. So 0, 1, 2, etc. Okay. So if you are interested in events like this, let's say AI is the event that there are I individuals. Well, this means your event is just a singleton, right? I. So the event that there are no individuals, the event that there is just one individual, the event that there are two individuals, etc., etc. So if these are the interesting events for you, in other words, if you collect them in a collection like this, so in other words, if this is your collection of questions, okay, always be careful about those brackets, okay? What is a set? What is a collection of sets? What is a point? Always be careful about these. So now this A is a collection of sets. So what is a sigma algebra generated by this collection? For sure, this is a sigma algebra, and it is a subset of the power set. It's a subsigma algebra of the power set. Do you think there is a set, there is an event that is not in the sigma algebra generated by A? You think no. Why?
Looks like it's sigma algebra is equal to the power.
So if we're considering events like singleton 0, singleton 1, singleton 2, well, they create all the sets. I can create every possible subset of Z plus just by taking countable unions and intersections of sets in A, right? That's what you're saying. So, but let's prove it. Let's prove it. That's good intuition. Indeed, sigma A is equal to Z plus. Well, this part is trivial, right? It's already a subsigma algebra of the power set. So let's show it. Let's check A in 2 to Z plus implies A in sigma of script A. Well, A is in 2 to the power Z plus means what? A is a subset of Z plus. What is a property of a subset of Z plus? What is the property of Z plus? What kind of a set is this? Z plus is a finite set? No. Countable set, right? Countably infinite set. So since Z plus is countable, A must be countable. Well, countable, finite, or countably infinite, right? Z plus is infinite, but its subset can still be finite. Anyway, we don't care. Since it's a countable set, I can write any countable set as a union of countable sets. What kind of sets? how can I write a countable set as a countable union? Exactly. Just consider every element as a set, as a singleton, just by putting brackets. So write A as union of i's, where I belongs to A. This is countable, so is a countable union. This is a countable union. I'm really using the fact that Z plus is a countable set. Okay? Don't do it with R. It's wrong. So now this is an A, right? This is an A by definition. And therefore, if I have sets in A and countable union of sets in A, it must be in A again. Countable union of sets in A. Does it have to be in A again? No. It's in sigma A. The countable union of sets in A can be in sigma A, but doesn't have to be in A itself. Because the one that is a sigma algebra is sigma A, not A. Okay? So this is in A, so it is also in sigma A. And I have, this is a sigma algebra. I have sets in a sigma algebra. Their countable union is an element of the sigma algebra. So that's it. A is in the sigma algebra generated by script A. Therefore, so 2 to Z plus equals sigma A. Or let me write it this way. And the opposite part was already clear, so we're done. A similar example, tossing a coin n times, remember. So this was the sample space consisting of 0, 1, cross 0, 1, cross 0, 1. Well, just finitely many times, so let me write it this way. Okay, or in other words, if you write omega this way, each component is either 0 or 1. Now, let's create some events. AI is the event that the ith toss gives heads. So it is the event that we have omega I is 1. So set of n tuples whose ith component is 1. Okay? So now, what is the sigma algebra generated by A1, A2, A3, A4, A5, AN, let me say? Okay. Again, you can check that this is equal to 2 to power omega. This means you can write down any event as unions, intersections of events in the collection A. Because, hey, A1 is the event that the first toss gives you heads, and A5 is the event that the fifth toss gives you heads. So if you have A1 to A5, if you can answer questions about A1 to A5, you can answer any question about the random experiment, right? You have access to all possibilities. What is counterintuitive again, is the infinite version of this game. Tossing a coin forever. So, forever. So remember, this was 0, 1 to n, which means set of all sequences, omega 1, omega 2, we don't stop, omega I in 0, 1, for all I in n. Let's do the same. Let AI be the event that the ith toss gives heads, meaning that this is the set of sequences for which the ith component is 1. Okay, now define again A as the collection of A1, A2, but now we don't stop. In this case, the sigma algebra generated by A, the collection script A, is a strict subset of 2 to omega. Very counterintuitive. Although it looks like you have access to everything in the random experiment. You know the result of the first toss. You know the result of the second toss individually. Apparently, this is a strict subset of the power set of your sample space. This is not a trivial result. We cannot check it just like we did the bacteria example. So we're not going to do it. But I just want to warn you that it's not always intuition works very well. Sometimes you have counterintuitive results. So this is one of the cases. Another counterintuitive thing about this was that this set omega is uncountable. Remember from last time? Omega here is uncountable. It's not countable. So this is another non-intuitive thing, maybe. So non-trivial fact. I mean, you can look at books or some online sources for its proof, but it's not worth spending some half an hour or so to prove this result, so let's skip it. Finally, we are discussing the example of the real line. Motion on R. Okay, remember this was a bee or an insect moving randomly on the line. So its position was a random number on the real line. So we took this as omega. And now we are interested in the following event. A is the event that the position is strictly between A and B, where A is here, B is here. So it is indeed the open interval AB. Okay, that's a very natural event, right? You would want to know if your position is between the 0 point or the first kilometer, right? That's a very natural question you'd like to be able to answer. So let's define A, script A, as the collection of all such intervals. What is the sigma algebra generated by A? What is the sigma algebra generated by A? Let me also write A and B are real numbers. Okay. Again, this is a non-trivial fact that this is a strict subset of the power set of the real line. And this sigma A is a very important sigma algebra. It is called the Borel sigma algebra on the real line. So I'm going to state it as a definition rather than a little part of the example. So the sigma algebra BR defined as sigma of the open intervals is called the Borel sigma algebra on R. That is the convenient sigma algebra on the real line. As I said last time on Tuesday, the power set is usually too big for a nice probability theory. There are mathematical reasons behind that. And this is really the part where I'd like to repeat this result. So if you'd like to do probability theory or measure theory on the power set, you will get into trouble very easily. But on this Borel sigma algebra, you don't have those troubles. I'm going to state a negative result when we come to discuss measures and probabilities. So hopefully that negative result will convince you. But for now, I'd like to say that this is the important sigma algebra on the real line. We will always deal with the Borel sigma algebra on the real line. Okay? So it is the very important sigma algebra for us. And indeed, whenever we talk about the real line and we need a sigma algebra on the real line, it is always the Borel sigma algebra. Okay? First of all, why? Is it enough? Is it rich enough? The answer is yes. So let me write it. BR is very rich. Okay? And now we're going to prove why this is so rich. The Borel sigma algebra BR on R is generated by each of the following collections. Okay, so I'm gonna cheat from my list because there are so many collections and I wanna index them in the right way. I mean, not to confuse myself. So the first one is the collection that is already mentioned in the definition, right? So it is generated by open intervals that are bounded from above and below. It is also generated by closed intervals that are bounded from above and below. Half opens, half open, half closed, right? The other way around. So now what else? We covered all 4 cases, but now there are open-ended intervals like this. So now we have A up to infinity. These are also collections that generate the Borel sigma algebra. The closed version. And finally, we have minus infinity to B and minus infinity to B included. Wow, that's a big result. There is a lot to prove. And let me also say, in particular, BR, the Borel sigma algebra on R, includes all intervals and singletons. Singleton means a set consisting of a single point. So why does it include singletons? Well, if you look at this part, A to B closed, just take A equals B, you have a singleton, okay? So they're part of the collection. And I did not put anything like A less than B. Just make a convention here. Things like 2 to minus 1 is considered to be empty set. So if you see things like 2 to minus 1, it's just stupid. Just take it empty set, okay? Just as a convention. I didn't want to write A less than B every time. Okay, very good. So let's first look at this result again. What does this say? Anybody who wants to restate this result? So what does it mean? BR is generated by each of the following collections. What does that mean? Can you write it as an equation? Can you state this result as an equation with using A1, A2, etc.? Line equation? What do you mean? Like a equation, equality of a lot of things, right? So we know that the Borel sigma algebra is already generated by A1, right? BR is equal to sigma A1. This is definition. What we are saying here is that BR is equal to sigma of A1, sigma of A2, also sigma of A3, up to sigma of A8. That's what we are trying to say. So we say here that maybe not a proof, as a remark. Okay. Borel sigma algebra on R, which is already defined as sigma of A1, but we're claiming that it is equal to sigma of A2 up to sigma of A8. Let's first understand what the statement says. And now we need to prove it. Of course, it's going to be a long proof. The longest possible proof perhaps would be to take any two of those collections, let's say A2 and A6, and start trying to prove that sigma of A2 is equal to sigma of A6. Do it. Sigma of A1 equals sigma of A6. Do it. Like, choose 2 out of those 8 collections and write down a proof for every single pair. And this would cost you probably days, right? So we're not going to do that. What we can do instead is to create a chain of inclusions. So if I want to prove A equals B equals C, what I can do is to prove A is a subset of B is a subset of C is a subset of A, and then I would be done. So this is what we're going to do now. So let's try to find out a chain here. Let me start from 1. Let me start from 1. So that's an open interval from both sides. Probably number 3 would be an easy pass for me. At least the right side stays the same, but the left changes. So let me pass to 3. Okay, so this means for the proof, let's show sigma A1 is a subset of sigma A3, is a subset of, maybe now that I have A, this part closed, but this part changes, I can pass to 2. Now I have A and B, B closed, I can pass to 4. B's are the same, A changes. Let me write it. 1, 3, 2, 4. maybe 4 to, well, now we're left with those. I can either go to 5, right, or maybe 8. Let's go to 8. Let's go to 8. And then, if you compare 8 and 5, they are the complements of each other in a way, right? So minus infinity to a point included, versus a point not included up to infinity. So if I go to 5, this would be an easy job. Then maybe 5 to 6. And 6 and 7 are like complements because you see this part is included here, this part is not included. This is going to minus infinity, this is going to plus infinity. And then I have to go back to 1. Okay? Which is fine. B parts are similar. This part changes. So let me write this. 4, 8, 5, 4, 8, 5, 5 and 6. Yeah. 6, 7, and again back to 1. So if we can complete this program, the proof would be complete. And even this is too time consuming for a lecture, so I'm just going to do one part and leave the others for you as a homework exercise. How is that? Okay. But did you get the idea of this proof? We have to come up with a structure before attempting the proof, right? So this is the structure. So let's prove maybe sigma A1 is a subset of sigma A3. Okay? Let's attempt the proof. Let A be in sigma A1. I'd like to show A is in also sigma A3. Well, A is in sigma A1. What does that mean? I have no idea. I have no idea. So one of the peculiarities of sigma algebras is that, generated sigma algebras is that you don't have like a general form, like a closed form of a set in a sigma algebra. Okay? That's why people usually think sigma algebras are awful. They're very difficult to deal with. Okay? But what we can do is to at least start with, so what can I say? What can I say about A? And the answer is not much. But let's start with something easier. Let's start with something that has a concrete structure. Let us take A in A3 and show A is in sigma A, sorry, not A3, A1, and show that it's in sigma A3. I know that sigma A3 includes countable unions, intersections, complements, etc., of the sets in A3. But still, there are many other sets whose exact structure I cannot write down. Okay? So if you give me a countable union of sets in A3, I can tell you that the union is in sigma A3. There is no problem with that. The difficulty is that if you just take a generic set from sigma A3, there is no special structure for that. That's the problem. Okay? So now let's write down A. Well, A is in A1, so A is just, note that A is A to B for some AB with A less than B. Let's include the empty case. Let's not include the empty case. Let's deal with the meaningful case. Anyway, so can I write AB as a union, intersection, etc., of sets of this form? The answer is yes. So I have A here, I have B here, and I can write down this using sets of this form. So closed from the left, open from the right. So the right I'm not going to change. So what should I do? What should I do? Take A complement. What is it? From minus infinity to A.
No, just for A3, so from B to A. For omega A3.
What did you say again?
For omega A3?
Omega in A3?
Yes.
Okay.
From A to B, but A included, B excluded. Exclude A.
But if you exclude A, you're not using a set in A3. So we'd like to, here's what we're trying to do. We'd like to be able to write down A to B of this form as a countable union or intersection of sets of this form. They don't have to be A and B exactly. I can replace A and B with different numbers, but the point is that this left part has to be closed and the right part has to be open. Okay? Yes?
We can take an internal sequence like closed A plus 1 over n with B.
So let's do it. A plus 1 over n is somewhere here, right? If n is large enough, A is very close to A plus 1 over n. So the idea is that why don't we just look at this interval? Why don't we just look at this interval? As n increases, we will get closer and closer to here. But we will always exclude A, because A plus 1 over n, no matter what n is always strictly greater than A. So let me add this 1 over n here. Let me write it as a union. This set is smaller than A to B, so I have to take a union. Gets larger, larger, and larger, but never really touches A. If you are not convinced, let's show it. Okay? At least this is our claim. And now the proof of the claim. So if X is in the union A plus 1 over n to B, then X is between A plus 1 over n to B for some n. Since A is less than A plus 1 over n, we also have X between A and B. So this part of the inequality is shown. Conversely, let X be in A to B, but assume X is not in the union. So this means X is in the complement of this set, which is the intersection of minus infinity to A plus 1 over n, right? 1 to infinity. So X is less than, well, I also need, X is less than A plus 1 over n for all n. And this means if I let n go to infinity, I would get X less equal A, which contradicts A greater than A. Okay? Okay, so proof of the claim is done. Now we're more convinced, hopefully. Okay? So this is a little exercise that you should also do yourself and convince yourself that this is really the case. Try with other things. Try intersections. Try intersection with a minus 1 over n and see why it fails, okay? Just do it at home. It's an important exercise. But anyway, if we are able to do it, we're done because it's the union of those things, and each of them is in A3, well, which means it's also in sigma A3, and it's a countable union of things in sigma A3, so this is also in sigma A3, and we're done. What did we do? We took a set in A1 and proved that it is in sigma A3. So let me write it here. A1 is a subset of sigma A3. Now I'd like to conclude sigma A1 is also a subset of sigma A3. We use the following lemma. Okay, that's a special lemma. Okay, so let A be a collection of subsets of omega and F a sigma algebra on omega. Then, if A is a subset of F, this implies the sigma algebra generated by A is also a subset of F, which is really what we need to pass from here to here. Okay? How should we argue about the proof of this lemma? So A is a subset of F, okay? Since A is a subset of F, F is a sigma algebra containing A. So it is larger than the smallest sigma algebra containing A. This is precisely sigma A is a subset of F. Okay? Let's rethink about this lemma, okay? You have a collection of subsets, which is a subcollection of a sigma algebra. This also implies that the sigma algebra that covers A also covers the sigma algebra generated by A. Okay? So you have a sigma algebra containing A, but this is already one of the sigma algebras containing A. So the smallest sigma algebra containing A is certainly smaller than F, because F is one of the sigma algebras that we intersected when defining sigma A. So for sure it is larger. Just like the power set. Think about the power set, right? Sorry?
Can it be equal?
Well, of course. If A is a sigma algebra, and A is equal to F, and then sigma is equal to F as well. Yeah. But in general, they are not equal. Okay? So this does the job. If we have A1 is part of sigma A3, we also have sigma A1 is part of sigma A3, and we're done with this proof. Okay? So let me put a check here. And the rest of the proof is homework. So now we have a sigma algebra on the real line. A very rich sigma algebra, smaller than the power set, and it's going to be very convenient. We're going to define the so-called Lebesgue measure on this Borel sigma algebra. Okay? But since we're at it, I'd like to say a few more things. So, okay, this is the sigma algebra on the real line. How about sigma algebras on intervals? What if I'm just interested in 0 to 1, like in the milk example? Remember the milk example. The sample space was the interval 0 to 1. What if I need a sigma algebra, like the Borel sigma algebra, on the interval 0, 1? What if I'm not interested in the whole real line, but I'm just interested in a special interval? Can I still have a sigma algebra on an interval? The answer is yes. And the way to construct a sigma algebra on an interval is as follows. Just take all Borel sets. So these sets in the Borel sigma algebra are called Borel sets. Just take Borel sets, intersect them with the interval 0, 1. You get your subsets, your Borel sets of 0, 1 interval. So this idea to restricting or tracing Borel sets into a smaller set is called tracing, okay? We're going to call it tracing. So let me write down a definition, okay? Let omega f be a measurable space and a non-empty set. The collection, I should actually write it as a proposition, sorry. The collection A, which is defined as A intersection F, where F is taken from F, script F, is a sigma algebra on A, and it is called the trace of F on A. So before the proof, here's the application. Take omega f as the real line with the Borel sigma algebra, and take A to be 0, 1. The trace is what? 0, 1 intersected with a Borel set is called the Borel sigma algebra on 0, 1. Denoted like this. Just take any other similarly. We may define the Borel sigma algebra on any subset of the real line. A subset of. Just take Borel sets of the real line, intersect them with your smaller space of interest. You get a new sigma algebra. Okay? Sure.
Is the proof of the proposition straightforward or just?
We're going to do it now. Before we go, we're going to do it very shortly. It's not difficult. We just need to check the definition of sigma algebra. We have to be careful because this is a sigma algebra on A, not the full space, not omega. So proof. Let's prove A is a sigma algebra on A. Of course, we proceed in 3 steps. First, we have to show that A is in script A, because A is now the sample space, right? We are saying script A is a sigma algebra on A. Okay? But why is it in A? Well, because I can always write it as an intersection with the full space omega. Since omega is in F. F is a sigma algebra on omega. Let B be in the script A. We'd like to show that we'll show the complement of B in A, that is A minus B, is in script A. Is in script A. Okay? So, since B is in A, we have B equals A intersection F for some F in script F. So let's look at A intersection B, okay? A difference B, which is A intersection B complement. Now it's all set algebra, right? Let's write down what B is. And now this is A complement union F complement. So this is A intersection A complement union A intersection F complement. And A intersection A complement is just empty set. So this is A intersection F complement, which is in script A because this is in F. Okay? Just definition checking. No new arguments. And the last property we should check is the countable closure under countable unions. So last property, let B1, B2, etc. in A. So B1 equals A intersection F1, B2 equals A intersection F2, etc. for some F1, F2, etc. in F. We'd like to prove that the union of BI's is in A. So what is the union of BI's? Well, BI is just A intersection Fi. Therefore, it is A intersection the union of Fi's. Again, this is set algebra, right? Set operations. And this is in F because F is a sigma algebra. Fi's are in script F. Therefore, it is of the form A intersection some set in script F. So it is in script F, script A. So we're done. So A is a sigma algebra on A. So this way, we can create sigma algebras on intervals, on weird sets, just by tracing, just by intersecting the Borel subsets of the real line with our smaller set of interest. That's the punchline. Okay? And we're done for today. See you next Tuesday. Thank you.